The fastest object ever made by humans is NASA's Parker Solar Probe, traveling at a staggering 430,000 miles per hour. That's fast enough to fly from New York to Tokyo in less than a minute. And yet, in cosmic terms, it's still painfully slow. At that speed, it would take over 6,700 years to reach Proxima Centauri, our nearest star. Now imagine reaching Mars in just 45 days, or flying past the edge of our solar system in under a decade. These ideas are no longer just science fiction. They're grounded in real engineering, funded projects, and active research. Today, we're diving deep into the most advanced propulsion systems in development, how they could change space exploration forever, and what it will take to bring these revolutionary engines to life. Let's begin by understanding why propulsion matters so much. Traditional chemical rockets, like those used on the Apollo missions or SpaceX's Falcon 9, burn massive amounts of fuel to achieve high thrust over short durations. They're great for launching from Earth's surface, but extremely inefficient for long-distance travel. The fuel requirements grow exponentially with mission length and payload weight, which is one of the biggest bottlenecks in current spaceflight design. Even a mission to Mars requires carrying tons of fuel just to slow down upon arrival, or to launch a return mission back to Earth. This is known as the tyranny of the rocket equation. Every kilogram of mass requires more fuel, which adds more mass, which then needs even more fuel. It's a vicious cycle that limits the range and feasibility of long-term human spaceflight. To break free from this loop, engineers and scientists are developing radically different propulsion systems. Let's start with ion propulsion. Instead of burning fuel, ion drives use electricity, usually from solar panels, to ionize a gas like xenon and accelerate it using electric or magnetic fields. The thrust is incredibly low, but it builds up over time. NASA's Dawn spacecraft, which used an ion engine, was able to orbit multiple asteroids in the asteroid belt, something no chemical rocket could do. The trade-off is patience. While slow to start, ion propulsion can reach incredible speeds over time and is perfect for unmanned missions. Next up, nuclear thermal propulsion, or NTP. This technology uses a small nuclear reactor to heat liquid hydrogen, which then expands and exits through a nozzle to create thrust. NTP can deliver twice the efficiency of chemical rockets and significantly reduce travel time to Mars. It's also one of the most realistic technologies that could be deployed within the next decade. NASA and DARPA are planning a demonstration by 2027. Unlike ion drives, NTP offers both high efficiency and enough thrust to carry heavy payloads, making it ideal for human missions. There's also nuclear electric propulsion, which uses a reactor to generate electricity for ion engines. This combo offers the long burn time of ion drives with the energy density of nuclear power. It's an excellent candidate for deep space missions, where solar energy becomes too weak to power spacecraft effectively. Even more ambitious is fusion propulsion. This concept aims to harness the same reactions that power the sun, fusing hydrogen atoms to release massive amounts of energy. Companies like Helicity Space and NASA's Princeton Plasma Physics Lab are exploring this technology. Fusion could deliver unmatched thrust and efficiency, potentially cutting travel time to outer planets and beyond to just months. The challenge is, we haven't even built a fusion reactor that produces more power than it consumes here on Earth. But progress is being made, and the implications for spaceflight are enormous. Then there are the true sci-fi contenders, antimatter engines and warp drives. Antimatter engines would annihilate matter and antimatter particles to release pure energy. Einstein's famous EXMC2 in full effect. Just a few grams of antimatter could power an entire mission to Saturn. The problem? Antimatter is extremely expensive and unstable. We can only produce nanograms at a time in particle accelerators, and storing it safely is still a major hurdle. And warp drives, like the Alcubierre drive, would contract space in front of a spacecraft and expand it behind, moving the ship without technically violating the speed of light. While currently theoretical, physicists have shown that the math might check out under specific conditions. Still, we're likely centuries away from anything resembling this concept. So where does that leave us? The most promising and realistic near-term technology is nuclear thermal propulsion. With proven science, active funding, and prototypes on the horizon, it's the bridge between what we can do now and what we dream of doing in the future. A nuclear-powered spacecraft could get humans to Mars in just 45 days, dramatically reducing radiation exposure, life support requirements, and cost. That's not just fast, it's transformational. When you think about the scale of our galaxy and the challenges ahead, it's clear we need these breakthroughs. The future of space travel won't be built on the fumes of yesterday's technology. It'll be driven by science that reshapes our place in the universe. From high-efficiency ion drives to the mind-bending possibilities of warp engines, propulsion is the key to our destiny among the stars. Which of these systems do you think will define the next 100 years of space exploration? Drop a comment below and let's talk about it. And if you're curious how these engines might power the first human colonies on Mars or beyond, watch our next video on the future of interplanetary colonization. Subscribe to keep traveling through space and time with us.